Hi students, good evening to all of you. In today's session we'll be basically looking at your indicator diagram. Alright, this is the second lecture on the series of your laws of thermodynamics. In the first lecture, my dear students, we had studied about the first law of thermodynamics. Now the first law of thermodynamics basically talks about the conservation of energy. That means whatever heat you kind of provide to a system, it uses it in two ways. Number one, it does increase the internal energy of the gas and the gas is able to do some external work. Alright, now here in this particular topic of indicator diagram, it is nothing but it's a graph that is plotted between pressure and the volume of the gas. Clear? Between the pressure and the volume. So it helps us in understanding generally how it was invented. All right, it was used to study the efficiency of a engine. All right, students. Now here PV graph has got other utilities also, but however we will restrict everything to your thermodynamics. So it helps us in understanding a thermodynamic process as such. Okay. So there are certain elements that we are going to go ahead and check out. So let's get started, my dear students, with the concept of indicator diagram. Now, generally, we kind of study the indicator diagram with respect to a thermodynamic process out here. So let's say we have got a thermodynamic process in which we have a beaker, it is filled up with gas, it is being heated up with certain amount of heat. All right, so at a certain stage T1, what is going to happen? The gas has got certain thermodynamic variables which are like its pressure P1, volume V1 and temperature T1. You keep on heating this particular system. At a later time T, what is going to happen? The thermodynamic variables are basically going to change. So the first state was represented by, let's say, A, and the second state, when its pressure became P2, volume became V2 and temperature became T2, it was represented by the state B. Now what we do is basically represent this particular variable of the gas in a graph between pressure and volume. Alright, so here exactly that we had P1 V1, so it is representing your state A, my dear students, and it went to state B after a certain time through a given thermodynamic process. Now those we are going to discuss, the different thermodynamic processes we are going to discuss in our next lecture. So we are not focusing how it actually went from A to B. We just saying that at a certain stage A, all right, it was at a certain time T, it was at stage A, at a certain later time in T, it was at stage B, my dear students. Now, what are the information that we want to actually extract, or what is the utility of this particular curve, okay, or this graph? It helps us in calculating the work done during a thermodynamic process. It also helps us to extract information about the change in internal energy. All right. Now, in the last lecture, before we go ahead, we will like to see another utility of the indicator diagram, which is kind of very close to our heart, because the very fact that the PV graph, it helps us in understanding the performance of a heart, okay, over a given cycle. All right, students. So, well, this is not related to our syllabus, but knowing one of its utility can always be helpful. All right, students. So it kind of helps us in understanding the efficiency of the performance of the heart as well over a given cycle. All right. But let us restrict ourselves to thermodynamics out here. Now in thermodynamics, in the first law, we had three elements that we had looked at. That is the heat provided, delta Q, change in internal energy, delta U, and delta W is the amount of work done. Alright, students. So anyways, delta Q at constant pressure is different. It is N Cp delta T, where N is the number of moles, Cp is the molar specific heat at constant pressure, and delta T is the change in temperature. Constant volume, we have got it replaced by Cv. Alright. Students, this value is going to be different from here, because whatever heat you are going to provide at constant pressure, it is going to do two things, my dear students. Increase in internal energy plus work done. Alright. But however, at constant volume, if you see, last time we had looked at that the work done alright, is equals to P delta V, alright. So if you are doing it at constant volume, then what is going to happen is your delta V is going to be 0. As a result of which the work done is 0, so the delta Q is going to be different. Generally, if you see, for the same change in temperature for a given gas, the heat supplied at constant pressure is always greater than the heat supplied at constant volume. Okay, so this is an information which is useful that we carried from our first lecture, that is on the first law of thermodynamics. The next element that we kind of saw was the change in internal energy, which is kind of given as NCV delta T. That is, it is a function of change in temperature. If the temperature changes, there will be change in the internal energy. However, there is no change in temperature, the internal energy is going to remain constant. There are two formulas by which we can actually represent it. That is NCV delta T or NFR by 2 into delta T, where F is, my dear students, is the degree of freedom. Clear? And delta T, change in temperature, R, we know it, is the universal gas constant. So these are the two formulas which helps us in calculating your delta U. Okay. Next element is the work done. Clear? Now, how do we find out the work done? We know it's equals to P delta V. Right? Now, students, using the indicator diagram, the process of finding out the work in a thermodynamic system becomes actually very easy. Okay, let us see this. Now we are taking one of these graphs. Clear? In this, it is kind of very imperative that in the y-axis you've got pressure, on the x-axis you've got volume. So let's say the thermodynamic process starts from this point out here and it kind of reaches here through this process. Clear? Then work done, we studied, is P delta V. So P is nothing but this value and delta V is the change in the volume as the gas goes from the initial state to the final state out here. If you look at it carefully, P into delta V, P is like the length, delta V is like the breadth. So length into breadth, we kind of get the area under the curve. Alright? So you kind of get the area under the curve. So area under the PV curve gives us basically the work done. Alright. Now this is kind of very simple to imagine, but however, let's say we have got a different case in which the pressure is not constant over the entire process. Then what do we do in that case? Let's say it goes from state A to state B. So in this particular case, my dear students, we use the concept of integration. So we kind of divide all these zones into smaller strips, all right, and we find out the total area under the curve. We find out the total area under the curve by taking the summation of the areas of all these, which is kind of given by this process of integration, and it really makes our life very, very simple in solving the questions of indicator diagram in the examination. All right, let us look at how. Now, there are certain aspects before we go down to the numericals, my dear students, few problems that we want to look at. Let us try and understand the sign convention, right, that we can actually extract from the indicator diagrams out here. So what did we study so far? We studied that in a PV curve, work done is basically area under the graph. If it is a straight line that we can see here the pressure is constant. Okay, in case the pressure is constant, it is simply P delta V, that is pressure into change in volume. Clear? And in this particular case, where the pressure is kind of not constant, we use the concept of integration to find out the work done. Clear? So given this, we know now that work done is area under the curve, right? So in case your expansion is taking place from point A to point B, that is in state A, my dear students, then we know that all these area that we are going to take here, all these area that we kind of take here is going to be positive. Why? Because expansion is taking place, delta V is actually positive, my dear students. Clear? However, in the case that the gas is undergoing compression, we are applying some external force because of which the gas is getting compressed. So in this case, my dear students, whatever area out here is, we are going to consider it to be negative, my dear students. Fine. So that is the idea behind work done, area under the curve, positive, expansion positive, compression, it kinds of becomes your negative. All right. Now, let us also look at one very interesting thing, that is the indicator diagram for cyclic process, wherein most of the questions are kind of related to your cyclic process in most of the competitive examinations that we have, whether it's JEE or whether it's kind of NEET. Okay. Now, what is basically a cyclic process, my dear students? The cyclic process is very simple to understand. Let me just explain this to you, that it kind of starts at a given point, undergoes multiple thermodynamic processes, like it goes from A to B through a certain thermodynamic process, then goes from B to C through another thermodynamic process, then comes from C to D through another one, and then finally comes back to point A. So, my dear students, this is the initial as well as the final state of the gas. Then, my dear students, what do I conclude from here? That is the initial thermodynamic variables, that is pressure, volume, temperature, and final thermodynamics variables, that is pressure, volume, temperature, both are same. That means there has been no change in the temperature of the system. Now, delta T is equals to what? 0. Students, if my delta T is actually 0, then what do I conclude from here? In any cyclic process, my change in internal energy will also be equals to 0, because we have studied that is my change in internal energy is NCV delta T, and since this quantity out here is 0, which tells me that my delta U will also be 0. Alright students, then what is going to be the first law of thermodynamics, or how is it going to be applicable for any cyclic process? I can see then my delta Q will be equals to delta U. Oh, sorry for that. Delta Q will be equals to delta W. Clear? So whatever heat is provided, it uses up in doing the work. Now, what is the work done in finding out, like, what is the work done in any kind of a cyclic process? Clear? Let us understand that aspect. Students, if you see AB, what we are doing? We are doing how to find out the work done in a cyclic process. Clear? So, if you look at AB, volume is constant, no work is done during AB. So, I can just plot it here, that work done during the process AB is kind of equals to 0. Alright. Similarly for CD, work done in the process CD is also equals to 0, because the volume kind of remains constant. What about BC? During BC, what is happening, my dear students? Expansion is taking place. So work done will be positive. And what is the work done? It's the area under the curve, this. Alright. So all these area that we are taking from the top to the axis, this is the work done during the process BC. Now what about DA? In the process DA, my dear students, the work done is negative because compression is taking place. So the work done is all this area. Alright, the work done is all this area. Now if you calculate the net work done in the entire cycle, the work done in the entire cycle, my dear students, it is nothing but area of just this region. That is the area enclosed within the circle is, my dear students, the work done in a cyclic process, and it is a very important information. Alright, so what is the work done in a cyclic process? The work done in a cyclic process is the area enclosed. Fine, so that kind of gets us a lot of information about the thermodynamic process with respect to the work done, change in internal energy is equal to 0, my dear students. Come on, let's move ahead and let us look at few other aspects of the indicator diagram out here, students. I hope you're enjoying the session out here. Let's get started with the numericals in a short while. So this is the first understanding of a question that we have, that is in which case, so we have an indicator diagram out here, all right, which goes from, let us look at this, which goes from the first state, initial state I or 1 or whatever you can call it as, and then it goes to state 2. From 1 to 2 it takes 3 different processes to go, A, B, C. Clear? Through A they have asked us what, in which case the heat absorbed will be maximum. Alright, now for that the basic understanding, my dear student, is that from 1 to 2, alright, that is from 1 to 2, the temperature at 1 and temperature at 2 is basically the same for all the 3 processes. Clear? So change in internal energy, whether it is going via process A, B or C, this is actually the same for all the 3 processes. Clear? Because of the very fact that internal energy is a state function, it depends on the initial and the final point. So here 1 and 2 point for the 3 processes being the same, the change in internal energy is basically the same. Alright, now the other aspect that we kind of look at here, so what I'll do is, let's remove this to here and let us draw a table of delta Q, delta U and delta W for process A, B and C. Clear, students? Now understand in which case is the work done maximum, because delta U is basically like, you know, if the value of the change, let's say, is kind of X, alright, then we have delta U is X for A process, B process and C process. Clear? So everything that is to judge delta Q is maximum in which case is basically depending on delta W, and delta W is maximum in which case? Delta W is nothing but it's the area under the curve. So if you look at process A, the area is going to be maximum during the entire process. Clear? So delta W is max for process A, it is minimum for process C. Then from here I can conclude my delta Q is going to be maximum for process A. I hope everybody understand this particular aspect. So kind of let's go ahead to the next numerical, my dear students, which is even further interesting. Fine? So we've got a question here in which it's a very simple question, my dear students, based on the concept of indicator diagram. A gas is taken from state 1 to state 2 along the path which is kind of shown here, that is 1 to 2. Clear? If 70 calorie of heat is extracted from the gas in the process, then what is the internal energy change of the system? Now one should be very careful, and this question kind of appeared in 2016 for JEE. Alright, though the question is kind of very simple, but it should be very noted out here that generally on the y-axis we have got pressure and the x-axis we have got volume, but we have just inverted the entire thing. On the y-axis they have put volume and on the x-axis they have put pressure, but that doesn't make anything change anything. All right, they have asked us what should be the change in the internal energy. Clear? Excuse me just a second, guys. Let us go back to the last slide. All right, so here it doesn't change anything. All right, see, it goes from 1 to 2. So the work done in this process is basically this area, that is the area under the curve. All right, by the way, students, in this case, as it goes from 1 to 2, is the work done going to be positive or negative? Has expansion taken place or compression? It is actually coming from 2.5 into 10 to the power minus 4 meter cube to 10 to the power minus 4 meter cube. So there is a compression out here. So work done is going to be what? Negative. Clear? So here this delta W is going to be negative, my dear students. Clear? Acha. Now next aspect. What is basically the area of this region? I can consider it, this entire thing, to be a trapezium. Notice it, this entire thing is a trapezium out here. So we can find out the area of the trapezium and get the work done. Clear? So let us just first calculate what is the area of this particular trapezium. So delta W, we can calculate here, is equal to half into sum of the parallel sides. That is, this is 2 into 10 to the power 5 plus 5 into 10 to the power 5. So we can calculate it here as 7 into 10 to the power 5 into, what is the distance between them? If you look at it, this is 2.5 minus 1. So that will become like 1.5 into 10 to the power minus 4. So my dear students, this becomes kind of 52. Alright, this becomes 52.5 joules. Clear? And is this work done positive or negative? We have discussed that already. It's a compression, so the work done is going to be negative. Clear? And in this process here, we have provided 70 calories of heat that is extracted. We have not provided, it is extracted from the system. Since it is extracted from the system, my dear students, whether it's going to be positive or negative, definitely negative, because we have taken it away. So now the first law of thermodynamics is going to be valid here, that is delta Q is equals to delta U plus delta W. So this, my dear students, 70 calories is equivalent to how many joules? It is approximately 294 joules. Clear? And you put it minus 294 because we have extracted this heat from the system. We need to calculate delta U, and work done is minus 52.5, and if I calculate it, delta U will come very close to what? Looks very simple. It comes to minus 242 joules if you kind of calculate it from here. So the option is C. Alright, so do not be tricked by the fact if volume is on the y-axis and pressure is on the x-axis. Concept still remains the same of what is the work done. It is area under this volume curve, okay, this PV curve. So this is the area right now, not this one. Alright students, so let's kind of move on to the next sum, my dear students. Stay focused and let us explain, kind of enjoy the next problem out here. So what do we have here, dear students? Very simple. This is very interesting now. Okay, it's getting interesting with each question. All right, so this is my initial, these are all indicator diagram based problems of previous year's JEE. All right students, so this is kind of my initial point and I am going to my final point. I can go from the initial to the final point through two different processes. Clear? That is, I can take this path or I can take this path. Now as per the question, when a system is taken from state I to state A along the path IAF, that is through this. Clear? It is found that Q is equals to 50 calories and work done is equals to 20 calories. So let me plot this entire thing in the path IAF. During IAF, Q is equals to 50 calorie and work done is equals to 20 calorie. Students, from this, can I calculate what will be the change in the internal energy in the process? Definitely, as per the first law of thermodynamics, we can easily find it out. It will be equals to 30 calorie. All right. Now, as we go from state I to F through this path, all right, that is in the process IBF. Students, can you tell me what will be the change in internal energy from in the path IBF? Isn't it going to be the same? Obviously, it is going to be the same because the initial and the final point for both the processes is basically the same. Clear? So for this process, your delta U will be 30 calorie. That we kind of calculated it from here because the change in internal energy remains the same for both the processes. Clear? Now, what will be, what is asked? You provided some heat, Q, 36 calories. Yes, my dear students, you've guessed the right answer. The work done in this process will be 6 calories. That is Q minus delta U, 36 minus 30, giving me 6 calories. All right, students, this is a very important concept. Like, you know, it is used multiple times regarding the change in internal energy. In the entire cyclic process, the change in internal energy is equal to 0. All right. However, we are going from the same initial point to the same final point. Then through any different processes we go from initial to the final point, the change in internal energy is going to remain the same for all the processes. So that is like the bottom line, the key important concept that we kind of learn here, and it is very, very useful for most of the questions. Okay. Chalo guys, let's kind of move ahead to the next question. What do we have here? In the next question, this is very interesting. This graph that we kind of look at here, that is 1 mole of a diatomic gas. Okay, diatomic. So we should be able to figure out what is the degree of freedom that we kind of learned in your kinetic theory of gases. Okay, so it's a diatomic, degree of freedom is going to be 5. We know that 3 translational, 2 rotational, total degree of freedom is 5. Clear? In the cyclic process ABC, the process BC is adiabatic. We don't need to understand whether it's adiabatic. We actually, like, you know, though it is being mentioned, a given thermodynamic process is given, all right, but let me tell you, we can do this question even without the information of what is isothermal process, what is adiabatic process, or isochoric or isobaric. Okay, let us look at how. Now importantly, they have given us the temperatures of these points, 400, 800, 600. It's a very smart way to do this particular question. Let me teach it to you guys. Okay, we need to choose the correct statement. Now correct statements are given out here. Focus, we need to analyze all of these. Fine. So the first statement is telling me the change in internal energy in the whole cyclic process is 250 R. Students, do you agree with this? No. We just studied the change in internal energy for any cyclic process should be equals to how much? It should be equals to 0. Isn't it, students? So I can easily cross away the first one, right? Acha. Second one, smart way to do it. The change in internal energy in the process CA. Students, CA as internal energy. Let us write down the equation for the internal energy. Clear? So delta U we know is NFR by 2 into delta T. So this internal energy change totally depends on the change in the temperature. Clear? So from C to A, tell me students, what will be your delta T? C to A. Get it? C to A? 400 minus 600 minus 200. So change in internal energy is going to be what? It's going to be negative. Whereas it is given here to be positive. Can that ever happen? No, it cannot happen. Change in internal energy should have been negative because the change in temperature is basically negative. So my option 2 is also not valid. Clear? Third one, AB. Students, A to B, if you see it, delta T, that is change in temperature, is basically positive because it is 800 minus 400. Delta T is always final temperature minus initial temperature. Final temperature is 800, initial temperature is 400. Cannot happen because out here delta T is positive, option is given as negative. This is also not possible, not possible, not possible. We are left out with only one option, my dear students, and I think that is the correct answer. You can check for it. Apply this particular formula here and check. If the value comes out to 500, it will definitely come out to 500. All right, because we have the 3 options wrong. Clear? Let's go to the last problem of this particular session, my dear students. I hope you are liking this so far. Fine guys, let's move ahead to the next question. As you can see, we did not use any of the information of the adiabatic thing here. It was an extra thing which was there to maybe confuse you up. All right. Anyways, in the following indicator diagram, the net amount of work done is, students, let me just give you this particular concept about the fact that in a cyclic process, that the final concept out here for indicator diagram, then all your basics are like kind of clear. In a cyclic process, my dear students, any cyclic process you take, I take another one. Let me take this out here. In a cyclic process, if it is a clockwise cycle and if it's an anti-clockwise cycle, all right, my dear students, if it is a clockwise cycle, work done will always be positive. If it's an anti-clockwise cycle, work done will always be negative. The simple explanation behind this is, see, you divide the cycle into two halves. So while going from this part to this part, work done is this much and there is expansion taking place, right? So this area is kind of positive, my dear students. Get it? Now look at this part, like kind of name it as AB. So while it goes from A to B, work done is positive. And while it comes from B to A, observe here, while it comes from B to A, my dear students, then you see the area under that zone is this. So this area and this part is basically negative. All right, that part is basically negative, right? So overall, if you can see during B to A, the work done is negative. Now area of definitely under AB is larger than the area of this blue section. Overall, the work done will be equal to positive because the area of this region is greater than the area of this region. Call it as A1, call it as A2. I can clearly see A1 is greater than A2 and A1 is positive and negative. So overall work done is positive. The vice versa thing kind of applies for a anti-clockwise thing, right? Now using this information, we kind of look at this problem out here which appeared in 2016. Okay, so what do we see here? In both the cycles that we can see here, both the cycles, kindly notice, in both the cycles it is anti-clockwise. See, it's anti-clockwise in both the cycles. If it is anti-clockwise in both the cycles, then definitely the net amount of work done is going to be negative. Clear? And if it was, let's say, hypothetically, let's say, if it was clockwise in this case and anti-clockwise in here, then since the area of the second circle is bigger than the area of the first circle, the net work done would be positive. All right, students. So that's it from today's session, my dear students. I hope you liked and enjoyed the concepts of your indicator diagram based problems. In the next session, that is on your thermodynamic processes, we are going to do even more questions using the concepts of indicator diagram. All right, but then they will be very much process oriented, like specific to adiabatic, like different stages of the cyclic process will have one say adiabatic, one say isothermal, one say different any other process basically. So we are going to look into that. All right, by the way, students, God bless you all. See you soon for the next lecture, that is on Sunday, that will be aired at 7 p.m. God bless you. Good night to all of you. Take care.